Welcome to another TSE single slider. Today's slide is about custom domains and DNS propagation. Specifically, we're going to talk about why updates to DNS records take time, usually many hours, to propagate across the internet. Let's set the stage with a client, which is typically something like a phone, tablet, or computer, and that client's DNS server. Let's say the client wants to visit checkout.example.com. The domain name checkout.example.com is not a routable address. It's more like a description of a place rather than instructions for how to get there. In order to actually find and communicate with checkout.example.com, the client needs an IP address it can route traffic to. That's what DNS is for. It resolves domain names to IP addresses. That process is called DNS resolution. The first step in DNS resolution is for the client to ask its DNS server where checkout.example.com is. For the sake of this example, let's assume this DNS server is brand new and has never looked up an IP address before. There's another DNS server out there somewhere which has the DNS records for checkout.example.com, but this DNS server doesn't know where to find it. A new DNS server only knows about root DNS servers. Root DNS servers are the backbone of DNS on the internet. It's not practical for root DNS servers to store every DNS record that exists, but they can tell you where to look for more information. Our DNS server just needs to figure out the right question to ask, and to do that, the domain name we're trying to find the IP address for needs to be broken down. Checkout.example.com is a subdomain, which is pretty specific, so the root DNS server wouldn't know anything about it. We can't ask about the subdomain, so we need to get less specific. This subdomain belongs to the example.com domain, but that's still too specific for a root DNS server. Even less specific is the top-level domain, or TLD. In this case, it's com, which is often referred to as .com. With the domain name broken down, the next step in the DNS resolution process is for our DNS server to ask one of the root DNS servers where the records for com domains are kept. The root DNS server pulls up the records in question and provides them to our DNS server. Let's pause for a moment and look at this DNS record. First, note that this is a simplified version of a DNS record which shows only the parts relevant to this scenario. The first line here has the domain name, which in this case is the com top-level domain. The second line tells us what type of record it is. In this case, the type is NS, which stands for name server, and indicates the record is telling us about a DNS server's IP address. Finally, the third line tells us what the TTL for the record is. TTL stands for time to live and defines how long a DNS record should be cached. This DNS record has a TTL of 172,800 seconds, which is 48 hours. We'll come back to TTLs later. Okay, now our DNS server has the IP address of a .com DNS server, which means we can find and communicate with it. The next step is to ask the .com DNS server where we can find the example.com DNS server. The com DNS server pulls up the record and provides it to our DNS server, and now we can find and talk to the example.com DNS server. Now we can finally ask the example.com DNS server what the IP address is for checkout.example.com and get the answer. Note the type of this DNS record. It's an A record, which stands for address. The previous records were of type NS and provided IP addresses for other DNS servers, but A records provide the IP address of a domain name. Now we have what we want, and our DNS server can answer the original query from the client by replying with the type A DNS record. At this point, the client can use the IP address to communicate with the server hosting checkout.example.com. Let's talk more about those TTL values. Note that the DNS records shown here have a mix of 24-hour and 48-hour TTLs. Those TTL values define how long the DNS records should be kept in a local cache before being considered out of date. As a result, both the client and its DNS server will keep the checkout.example.com DNS record cached for 24 hours from the time they receive it. That means if the client wants to find checkout.example.com again 12 hours later, it doesn't have to make a DNS request. The DNS record is still in its cache from the original request because the TTL still has 12 more hours to go. However, 36 hours later, after the TTL on the cached record has elapsed, the DNS record is considered out of date and is purged from the client's DNS cache. At that point, the client must once again reach out to its DNS server for help. The process starts the same way as the original request, with the client asking its DNS server where checkout.example.com is. However, the DNS server has less work to do because it can still use the example.com DNS record it cached 36 hours ago. That record is still valid because its 48-hour TTL has not yet elapsed, so the DNS server can use that IP address to contact the example.com DNS server and fetch the record without going through steps 2 through 5 from the original request. So what about updating a DNS record? As we've seen in this example, if a client or DNS server has a DNS record in its cache with a TTL that has not yet elapsed, that cached record will be used instead of querying for a new one. That means if you want to make an update to a DNS record, you'll need to wait for all outstanding TTLs to expire to ensure everyone is aware of the change. In other words, if the DNS record you're updating had a 48-hour TTL, you'll need to wait 48 hours for the cached records to expire before your update will be reflected everywhere. Note that your DNS provider may or may not allow you to set a custom TTL on your DNS records. Some people, in anticipation of an upcoming change, set their DNS record TTL to a low value so a later update will propagate quickly. Be careful though. Not all DNS servers or clients respect the TTL set on a DNS record. Some may keep the record cached beyond the TTL, so specifying a short TTL won't guarantee speedy propagation. Also note that a DNS change may start working for you, but that doesn't mean it's working for everyone. There are countless DNS servers spread all over the globe, and some of them may still be using stale DNS records even though the DNS server you're using is up to date. The safest course of action when making DNS updates is to plan ahead and assume your updates won't propagate fully for at least 48 to 72 hours. Setting the TTL on your records to a lower value ahead of the actual update can help, but if you want to ensure every single person will see your changes, you'll need to wait a few days. Now that you know how DNS propagation works, you can make DNS updates to things like custom domains for Stripe checkout with confidence.